Each of the resistors shown in the figure has a resistance R. Find the equivalent resistance between A and B. As you can see in this diagram that it is very symmetric in nature, and in such a situation sometimes current distribution method makes it easier to solve the equivalent resistance. So let me show you how to use this method of current distribution. Since we have to find equivalent resistance between point A and B, so let us suppose there is a battery connected between these two points. Okay, and suppose E is the EMF of this battery. So we'll extract I current from the positive terminal of the battery, and in the same manner the I current will enter to the negative terminal of the battery, as we know that. So when I current goes further from this resistance, then we can see that there are two halves of the circuit above the line AB and the other half is below the line AB, and both the halves are identical. So the current has to be distributed equally for upper and lower portion of the circuit. So I current becomes I by 2 for upper half and I by 2 for the lower half of the circuit. And one more thing, the point E and point F both are same since nothing is connected in between. So we know that these two resistances are connected in parallel, and also these two are connected in parallel. In the same manner, G and H both are the same point. So these two are in parallel, these two are in parallel. Anyway, so I current is coming from this branch and it gets equally divided for upper half and lower half of the circuit. So I by 2 for the upper half and I by 2 for the lower half. I by 2 current further gets divided equally between these two resistors by I by 4, I by 4, and in the same manner in the lower half also the current will be I by 4 and I by 4. Okay, so I by 2 current for the upper half, which gets further divided in two equal halves because these two resistances are connected in parallel and these two resistances are equal in magnitude. So equal current will be equally, the current will be equally divided between these two, and I by 4 becomes I by 2 now, and in the same manner I by 4 will be current through each resistor, and then again it gets added and becomes I by 2, and in the same manner it becomes I by 4 and I by 4 like that, and then again here it becomes I, and in the same manner the distribution will be there for the lower half of the circuit. Anyway, we don't need that basically because we have just introduced one variable I and we have distributed the current in the whole circuit because it was so much symmetric in nature. So we'll just find one loop to apply the Kirchhoff's law equation, and that's it. We'll get the answer. How? Let's start from the point B. So if we are at the point B, let us suppose that potential of the point B is VB. Okay, and we move this way. So we are moving from negative terminal of the battery towards the positive terminal of the battery. That means potential will grow by an amount which is equal to EMF of the battery. And in the same manner, we'll move further. So I current is going in this resistance R. So in the direction of current, potential will drop. So when we move from point A to the point F, the potential is dropped by an amount I into R. And from F, let's move towards A. So I by 4 current through the resistance R, that means potential will be dropped by I into R by 4 amount further. And in the same manner, we have reached the point A and move further and follow any of these two resistance. Let's go down. So further decrease in potential will be I into R by 4. We'll reach this point B. And then follow any of these two resistance. Let's say this way from B to G. We'll see that there is a further drop. We can see I R by 4 will be the further drop in the potential, and we have reached the point G. And in the same manner, we move towards B. In the direction of current, potential drops by IR and we reach the point B again. So it must be equal to the potential of the point. So VB and VB, these two gets cancelled, and what we get is E minus, here it is IR, here it is IR means 2IR and minus, this is 3 times IR by 4 and it is equal to 0. So this way we get E equal to, minus sign will go, if we take it to that side, it is 11 IR divided by 4. We can see that between point A and B we have attached a battery of EMF E and total current I is drawn from this battery. So what should be the equivalent resistance? We know that R equivalent is equal to total EMF divided by total current drawn from the circuit, means E by R. So equivalent resistance between points A and B in this case becomes E by I, which is 11 R by 4. So this is equivalent resistance. That means option D will be the correct option to this question.